So in this problem, we're given a system that looks something like this. We have a mass ma and a mass mb, both of which are hanging from a system of 3 identical pulleys, each with moment of inertia I and radius r. And we're asked, if we release the 2 masses, what will each of their accelerations a be? Now this problem looks a lot more complicated than it actually is. All we really have to do is the sum of the forces on each of the blocks and a sum of the torques on each of the pulleys so that we can figure out what each of their accelerations and angular accelerations are going to be, because this inextensible rope connects all of them, which means that we have a very strict relationship between what their accelerations and angular accelerations have to be. So in order to do that, I'm going to arbitrarily decide that MA is greater than MB, so that MA will fall and MB will rise. I'm then going to define downwards to be positive here, counterclockwise to be positive here, clockwise, counterclockwise, and up. I'm essentially defining my coordinate systems for each individual element along the direction that the rope is going to be moving. You can do this because the rope is there and because each of them are going to be moving sort of in this fashion. I'm also going to define the tension in this rope to be T1, this section to be T2, T3, and T4, and I'm going to label this pulley number 1, this pulley number 2, and this pulley number 3. So now I'm going to start doing the sum of the forces. So the forces on block A is going to be equal to MA times the acceleration A is equal to MAG minus T1. Sum of the forces on block B is going to be MB times A is equal to T4 minus MBG. So the torques on pulley 1 is going to be just R times T1 minus T2 is equal to I alpha. Now remember that acceleration is equal to R times alpha. That's what the relationship is that this rope is causing. Since the rope is not stretching, the acceleration of each of these blocks is going to be the same, and the angular acceleration of these blocks, or of these pulleys, is going to be related to it according to this formula. So this tells us that I alpha is equal to I over R times acceleration. So this tells us that this is equal to I over R times acceleration. So some of the torques on pulley 2 is also going to be equal to I over R times acceleration, and that's going to be R times T2 minus T3. Some of the torques on pulley 3 is going to be I over RA is equal to R times T3 minus T4. So now all we have to do to solve this system of equations is cancel out all of these tension terms. Now at first, if you just kind of look at the system, that seems like it should be very difficult. But in fact, if you notice, each tension term appears exactly twice with one positive term and one negative term. So we have T1 and T1, T2 and T2, T3 and T3, and T4 and T4. So all we have to do is multiply each of these acceleration equations in such a way that the tension terms will end up with a constant coefficient. If we can get all of these tension terms to have the same coefficient, then we can just add them all together, and all of the tension terms will cancel out. We won't have to worry about any of those unknowns, and we'll be able to just think about the acceleration. So all that's going to mean is that we divide by r for each of these things, and so we get I over r squared times acceleration. And for these guys, we're just going to leave them as they are, because the tensions are already have a coefficient of 1. So now we're going to add all of those together. We're going to get acceleration times ma plus mb. That's coming from these two terms right here. And then here we're going to add I over r squared, but there's going to be 3 of them because they all have the same I over r left-hand side. And so that's going to be plus 3I over r squared is equal to, now all of these tensions are going to cancel out, and we're going to be left with just ma times g minus mb times g. So now all we have to do is divide this term out. I'm going to factor out a factor of g just to make it look a little bit nicer. And so we get acceleration is equal to g times ma minus mb divided by ma plus mb plus 3I over r squared. So that is going to be our final answer. This is the acceleration that this block experiences downward and this block experiences